Okay, so we're looking for this blue area right here. And in order to get that, we are going to end up having to do some subtraction. So notice these are both below the x-axis. So technically what we're going to do is we're going to take this red area and we're going to take this blue area and we're going to subtract them. And that will leave us with this kind of greenish area because everything's going to be negative. So let's actually look at what this looks like, and I'm going to show you two separate ways of doing this. Right, so g of x is this like red line right here, and I'm going to make f of x blue because otherwise it's going to be kind of a pain in the butt. Okay, first thing we really need is those intersections. Now this one is fairly obviously 0, but you could double check that. And then we need to double check that this one, it looks like it's probably 2, 4, 6, 8, but let's double check. And really the only way to do that, or the way to do that, is to, and you can use technology 1000% for this if you wanted to, is you could just solve here. And so one solution is definitely x equals 0. That will work out. You could see that just 0 minus 4 is 0, 0, 0 minus 4. Check. Or we could actually solve for it, in which case we'd get 2 as it turns out. So here are two solutions. We have 0 to 2, which means that if I just wanted to get this like red triangle up here, one of the ways that I could do that is I could take the integral from 0 to 2 of x minus 4 dx. That's going to get me negative 6, which antiderivative of x is 1/2 x squared, 4 is 4x, and then I just plugged in 2, and I plugged in 0. That should get you a negative 6, which just means that this triangle right here has an area of 6, and it's negative because it's below the x-axis. If we do the same thing for the blue section, that will get us through all of this. And again, you could just plug this into a calculator, perfectly reasonable, but this is good practice for you. Negative 11 1/3. Then, always, top curve subtracting the lower curve, that would get me negative 6 minus negative 11 3/10, which is going to give me the positive answer of 5 1/3. That is one way of doing it. The other way of doing it, and this time I'll use like calculator style, is if you just do the integral from 0 to 2 of the red function, x minus 4 minus, because the red function is on top, it is the upper curve, minus the lower function, which is x squared minus 3x minus 4, all of that dx. You can, of course, simplify this because those x's, or at least one of those x's, you'd have 1x minus a negative 3, that would get us 4x. Negative 4 minus 4, those are going to simplify, and then you're just going to have negative x squared. And if you evaluate this using a calculator, you'll get the same thing. So again, if you're ever struggling with what is the upper curve and what's the lower curve, literally imagine drawing a straight line from the top to the bottom. Oh, it hit the red one first, and then it hit the blue one. Red one is upper, blue one is lower. Let me know if you have questions on that one. Okay, this one is a little interesting because you'll notice this section that we're looking for is not actually like bounded by both of the curves. If you only look at this piece right here, that has nothing to do with this red line. It has everything to do with this other red, purple, I don't know. It has to do with the curve, not the straight line. Whereas like this section over here is all about the red line. So this is actually going to be the sum of two different integrals. So this is tricksy, but what we're going to get is we need to first figure out where are those intersecting. So let's set those equal. Okay, so solution here is negative 1 plus or minus the square root of 17 over 2. And in this case, notice if we continue this over, there'd be another solution over here. That would be your minus, so we really only care about the plus version. So that right there, my friends, is x equals -1 plus the square root of 17 over 2, or about 1.562. So what we're going to end up doing here is we're going to want the integral from 0 to -1 plus the square root of 17 over 2 of x squared dx plus the integral from -1 plus the square root of 17 over 2 all the way out to this, which based on here is just going to be 4 of 4 minus x dx. Plug that into your calculator. So again, it's not the making it super complicated, it's being able to piece apart the diagram so that you can actually figure out what the pieces are that you want. Plug that into your calculator and you will get 4.24. Cool. Let me know if you have questions. Okay, this is a little bit more classic of one. We've got an upper curve, we've got a lower curve, we've got boundaries. It's going from 0 to 2. So in this case, it really is going to just be the integral from 0 to 2 of the upper curve, which in this case happens to be e to the x, minus the lower curve, which happens to be e to the -x dx. Plug that into your calculator, and you're good to go. Of course, if you'd rather do it the long way, antiderivative here would be e to the x plus e to the -x, just because that negative and that negative would end up working themselves out here. And then you'd evaluate that from 0 to 2. So you'd get e squared plus e to the -2, all of that minus e to the 0, which is 1, plus e to the -0, which is also 1, so this is going to be 2. You're going to have e squared plus 1 over e squared minus 2, which works out to be, well, works out to be that. There you go. Well, let me know what questions you have. Okay, so here's the problem where we have this funky, strange, weird area. If only we could just swap the axes, so literally rotate this thing, so y becomes down here and x goes up here, and luckily we can do that with an inverse. So what we're going to do is, instead of having y equal 3 over x, we're going to solve for x, so we can swap the axes basically. So then what we're going to do is we're going to multiply both sides by x. And we're going to get xy is equal to 3, and then x is equal to 3 divided by y, which you would get by dividing by y. Okay, now I want you to notice about this, that basically all this has done is we've ended up kind of swapping the x and the y. If you graph this, it will look like the exact same function. And now what we're going to do is we're going to do the integral from 1 to 3 of 3 over y dy. This is going to function just like an x would, except that we have y's. Just like if you switch the y, or an x for an m, so you have or dt, if you switch for a t, same thing happens. So in this case, our antiderivative is going to be 3 natural log of y, and we're going to evaluate from 1 to 3. So to do that, we're going to get 3 natural log of 3 minus 3 natural log of 1. Okay, so the natural log of 1 is 0, so this whole thing just goes away. So you are just left with, this is equal to 3 natural log of 3, because this bit right here is equal to 0. Let me know what questions you might have. I know this one was kind of strange, but basically you're just finding the inverse function by switching the x and the y, solving, and then integrating with respect to y as opposed to x. Okay, so we're going to sketch our lovely function here, which is x cubed. And x cubed kind of looks like that. Super beautiful drawing, just kidding. And we're just going to do it from the domain 0 to 1. So really we just care about 0 here out to about 1. So that's the thing that we're going to be rotating around the x-axis, which means we're going to end up with this kind of like funky, kind of pointy cone shape thing. Okay, and it wants us to find the volume. So the formula for the volume of a solid of revolution is from A to B. You're going to take pi times the function itself squared dx. So let's take our function and square it. So x cubed squared is going to be x to the 6th. So we're really just doing from 0 to 1 of pi times x to the 6th dx. The antiderivative, and like by all means plug this into a calculator, you're totally welcome to do that, but we're going to get pi times 1/7 x to the 7th, and we're going to evaluate from 0 to 1. So that would be pi times 1/7 of 1 to the 7th minus pi times 1/7 times 0 to the 7th, and that's 0. So you just get pi over 7. And that would be like units cubed, I guess. Let me know what questions you have, but that's really the gist of it. Okay, for number 3, what we've got is that we're going to get this teardrop shaped thing. That curve right there is equal to x over 100 times 900 minus x squared for 0 through 30. And when it says it's revolved by 2 pi radians, that's the same as 360 degrees. It just means that it went away all the way around the x-axis. Our first job is to find the antiderivative. So we're going to need some u substitution for that, but that's cool because we know what we're doing. Well, this function is decidedly too complicated for us to deal with unless we get rid of this squared. So what I'm going to do is I'm going to just distribute this. Because it is just this thing multiplied by this thing, I can square those things. They're not separated by like addition or anything. So this is going to be the same thing as x squared over 10,000 times 900 minus x squared, because that square root and the squared are just going to kind of simplify themselves out, dx. Now we should be able to actually deal with this, because in this case, and we don't even have to do u substitution, just kidding, we can just distribute. Amazing. Cool. Distributing. We just end up with 9x squared over 100 minus x to the 4th over 10,000. If you wanted to pull that 1 over 10,000 out front, you totally could have. I'm just going to leave it there. And then let's deal with this. X squared, the antiderivative of that is 1/3 x cubed. And the antiderivative of x to the 4th is going to be 1/5 x to the 5th. And they're still going to have their same coefficient, so dividing by 10,000 here and multiplying by 9 out of 100 here. Cool. Plus c. So this right here is the antiderivative of, for a. And then it says hence. Anytime you see the word hence, that means you're going to use the thing that you just did to find the volume of one earring. Now in this case, notice this didn't have that coefficient of pi, and because the formula for the volume of a solid is pi times the function, squared dx from a to b, we're going to have to take this whole thing and multiply it by pi for part B. So we're going to multiply everything here by pi, and then we can evaluate on the bounds, which they're telling us is from 0 to 30. So what I'm going to do is, and essentially what we're doing right now is we're going to get the integral from 0 to 30 of pi times my function, which was x over 100 times the square root of 900 minus x squared, that whole thing squared, dx. But we already found this part, so we know that the answer is going to be pi 900, 9 over 100, or times, I guess, 300, my bad, x cubed minus x to the 5th over 50,000. And then we're going to evaluate that from 0 to 30. By all means, use a calculator. You're totally welcome to. I'm just trying to draw some connections to you about this thing and the antiderivatives you can find. The actual answer here is going to be about 1017. Up here, I just showed you that this antiderivative evaluated at 30 would get us there, but absolutely 1000% if you want to just plug this whole thing in. You could say the pi times my whole function squared from 0 to 30, and notice we end up with the same answer. So the volume of one earring is 1017.88 centimeters, millimeters cubed. Cool. So then it says if 1 centimeter of gold weighs 19 grams and 1 gram of gold costs 30 pounds, I think, find the cost of gold used for the earring. Set this ratio up. And this is not calculus, this is just ratios. So 1 cubic centimeter is 19 grams, 1 gram is 30 pounds. Those grams are going to simplify and you'll get 1 cubic centimeter for 570 pounds. And if we then need 1,000, good golly. Sorry, just realized I made an assumption here. If this is 1 cubic centimeter, 1 by 1 by 1, 1 centimeter is 10 millimeters, so 10, 10, 10. 1 cubic centimeter is 1,000 millimeters. So in this case, we are going to need 1.01788, that's probably way too many sig digs, centimeters cubed of gold. So the question is, how much is that going to cost? If you go ahead and solve this ratio, you're going to end up, oh, come on, silly iPad, getting that x is equal to 570 times 1.01788, which gets us about 580. Cool. Let me know what questions you've got. So I assigned this one because it's, real lifey and stuff like that. But I will say I'm not super thrilled about the way they put it. So we got Hani, who thinks this bright red one. And the reason I'm saying that is because this is a half circle. And then we've got this parabola, which is Ahmed's. And Ahmed's is kind of this darker purpley brown something or whatever. It says choose the best metal. I think they mean for you to pick Hani just because it kind of matches a little bit better. If you picked Ahmed, I'm not going to hate on it. It's fine. But if we have chosen that Hani is a little bit better, which is a -4 plus the square root of 72 and 25/100 minus x squared. Then what we need to do is we need to square that whole thing because the radius squared. We need to multiply it by pi, and then we need to integrate it from -7.5 all the way up to 7.5. Okie doke. So let's do that. By all means, just plug this into a calculator. That is totally a reasonable thing to do. If you want to go through the exercise of actually squaring this, then you're going to do a lot of distributing and things like that. You can totally do it, but let's just use a calculator because you guys get to use calculators and it's totally fine. Well, we've got a ratio of 15 inches, or sorry, 15 units, my bad, units to 11 inches, because -7.5 up to 7.5, and we're saying inches. So if we cube that whole thing, cube it, we're gonna get 3,375 units cubed per 1,331 inches cubed. And we want to convert this guy, so we're going to say 558.5 units cubed per x inches cubed. Set these equal, oy vey, and solve. You get about 220 inches cubed. We could use a similar conversion of inches to centimeters, 1 inch per 254 centimeters. I just looked that up. Cube it, and you'd get your cubic, and then I just said, okay, well, if it's this many centimeters cubed per inch cubed, that would get you your total centimeters cubed. That last bit was just a reminder, because I'm sure they want you to actually do some conversions. So let me know if you have questions about that. Happy to go over that part. Okay, for 6b, we've got a region rotated a full 2 pi radians, or 360 degrees, around the x-axis. So first thing we're going to do is sketch it. That's always a brilliant idea. So here we have that. Y equals 0 is just that line right there. Y equals the natural log of x looks kind of like that. And then y equals 4 minus x squared is that one. And so the region that is bounded by all of those is roughly this one right there. So we've got a sketch. Now we're going to have to write down the integrals to quantify the volumes required. So we're going to end up doing the squaring and putting it around. But first we kind of got to piece this thing apart. And I'm going to argue that this is kind of a boundary point where we've got area 1 and then we've got area 2. And I believe that for area 1, if we can just figure out what that x value is, then it's just going to be that value. So we need that value and that value. Those are going to be our bounds. And just using a calculator here, we've got a -2 and we've got a 1. So that's a -2 and that's a 1. So area 1 is going to be from -2 to 1 of, and the whole thing, this whole section right here, area 1, is just bounded by that yellow curve, which is 4 minus x squared. So we're just going to do pi times 4 minus x squared dx. For area 2, that's this little kind of I don't know, pointy beak shaped region here. This is going to be the area between two curves. So what we're going to do is we're going to say it's the yellow minus the red. So in this case, and we need to find that intersection. So let me get that one for us. That is about 1.841. So this time we're going to add to this from 1 to 1.841 pi times, and then we're going to square this whole thing. And it's going to be the yellow, so 4 minus x squared minus the red, which is the natural log of x. Okay, so those are the integrals. And again, this part right here where you're kind of figuring all of this out and writing down the bounds and making it work, this is the bulk of the work. Now we're just going to plug this into a calculator and get it to tell us the answer, which happens to be 104.76 units cubed. And of course, when I said area, I meant volume. Let me know what questions you've got. Okay, here, so we've got a velocity formula, and we're supposed to get acceleration. Now remember, to go from velocity to acceleration, we're actually going to end up taking the derivative. So first thing I need to do is take the derivative. So v of t is e to the 2 sine of 3t cosine of 3t. And we have, my friends, a product rule problem. Throwback! So now we're going to take these each in part. We're going to call this u. We're going to call, actually, let's not do that. We'll call it m and n. We got m and n. So the product rule says y in this case is going to be m times n prime plus m prime times n. So let's get all of those. So for m, we have e to the 2 sine of 3t. M prime is going to be, this is a not a u substitution, but a chain rule problem. So we're going to write this as m equals e to the u equals 2 sine of 3t. U prime would be 6 cosine of 3t. The 6 comes from the fact that we're going to end up multiplying by that. And m prime would be e to the u. So then we're going to multiply those two things together. And we're going to get e to the 2 sine of 3t times 6 cosine of 3t. And that is just all of this for official, final, actual m prime. So this is kind of like fake m prime. Sorry, my bad. Okay, so now let's get n and n prime. Oh, that one's not so bad. N is just cosine of 3t, and then n prime in this case is going to be 3 times negative sine of 3t, or negative 3 sine of 3t. Whew! Okay, so we have, okay, so we got to get m, n prime, n. M times n prime plus n times m prime. Whew. Jeez. There's a lot just for the acceleration. But whatever, we got there. So this right here, my friends, is our lovely acceleration. A of t, I guess. So find an expression for the acceleration, and then when is this first equal to negative 5/10? Please, for the love of Pete, just graph it and we can find it that way. Having graphed it, so this purple is the acceleration because it's the derivative of velocity. And the first time that it hits a negative 1/2 of y is about 0.3 seconds in. So there's your answer. Then find an expression for the displacement of the particle. So now we've gone derivative, now let's go antiderivative. And I'm, just for sanity's sake, gonna move everything out of the way. We're gonna come over here. We're just gonna start over because it's not gonna be that bad. And this one actually is gonna be much better because it's not gonna be chain rule on other thing on other thing. Because we're gonna make this u. u is 2 sine of 3t, which means du dt is going to be 6 cosine of 3t. And heck, let's just divide by 6. Divide by 6. And we're going to get du over 6 dt equals cosine of 3t. So what we're going to do is we're just going to replace this cosine of 3t with that. So let's do it. Make more room this way. We're going to go over here. And I'm going to get the integral of e to the u, and I'm going to replace that cosine of 3t. So I'm going to write du over 6 dt dt. Those dt's are going to simplify, and we basically have now 1/6 e to the u du. Oh, how beautiful. The integral of e to the u is e to the u, so it's just going to be equal to 1/6 e to the u, which you happen to know is 2 sine of 3t, and then don't forget plus c. And then it says write down the exact value of the maximum displacement. So let's graph that and find the max. Here it is, and there's your max. Le voila. Let me know what questions you've got. Okay, so we've got this liquid that is cooling, and then it's going to get heated. And what's important to note is that this function that they give you is the change in temperature. So what this says is, like, if we're starting here, the change in temperature is getting more negative, and then it stops getting so negative and it starts getting less negative until it starts the change, and now it's starting to get heated. So here is where we're still cooling it and then heating. And I think that this might be one where it's really helpful to actually look at the antiderivative of this as well. So let's get a picture of that. Okay, so let's kind of make sense out of this. This is the antiderivative, and that's just 1/2 x squared gets you 1/3 x cubed, x to the 4x gets you 2x squared, and 8 gets you 8x. So like the derivative of this is this. This is just now straight up temperature. Like this is, the blue is telling me temperature, and the temperature is gonna be real negative, and then it starts getting less negative, and then it starts going positive. This is describing again how that temperature is changing. So down to about here, the temperature is getting more negative. So like this is steeper. This bottom here is actually an inflection point. And then it is starting to change to become less. So it's getting negative still. It's still negative, but it's getting negative less fast. It's like slowing down how negative it's getting. And then here, notice at this 0 that's there is when it starts getting positive. Okay. And starts becoming less negative, and then it gets actually positive. Okay. Okay, now let's actually look at the phrasing of these questions. So this says, when t is 8, find how many degrees higher the liquid is than when it was at t equals 0. Notice it doesn't say what's the temperature at t equals 8. All we can do is we can figure out how much higher it was than at t equals 0. So at t equals 0, according to this, our temperature at t of 0, the temperature at that time is also 0. At t equals 8, that's around about there. If you plugged it into that actual function right here, you would get the temperature is negative 21.3. So it's not actually higher, but we all know that the book is, dreadful. So it is 21.3 degrees cooler than at t equals 0. And then the total change in temperature, in this case, man, this book is just dreadful. In this case, we didn't actually have it. But let's say that we said 10, because that's really what I actually wanted here. Let's say like the change in between t equals 0 and t equals 10. Because then what you'd want is you'd want all of that plus that, right? At t equals 10, the temperature is about 50. So in this case, you'd say, well, here, to here, it just went up 50 degrees. But that's not what all of the liquid went through. It went all the way down to -50 and then all the way up. So it changed a total of 150 degrees. Sorry, not a great problem. I looked at it and I thought it was going to be good, but I was wrong. Unless I'm wrong, in which case tell me I made a mistake. That would be wonderful. I'm going to make a different video for this one, so look for it because I'm going to make it with Desmos. I want like active Desmos, not just screenshots. And actually, I'm going to do this one on Desmos too, so watch for that video.